Today I have simplifying radicals with multiplication and addition. Let's get rid of that. So the first problem is the fourth root of 81 to 81 times f to the 12th power. So how do we solve this one? We can start by breaking it up. The fourth root of 81 times the fourth root of f to the 12th power. So what number, let's start with this one. What number times itself 4 times is going to give us 81? That is going to be 3. 3 multiplied by itself 4 times will give us 81. So we have this one done. Now we have the fourth root of f to the 12th left to do. We can rewrite the fourth root of f to the 12th as, oops, sorry. Yep, my cat's here. Sorry about that. The fourth root of f to the 12th, we can rewrite it as the fourth root of f to the third multiplied by 4. Because this exponent times this exponent is going to be 12. So we have f to the fourth. We have the fourth root of f to the third power, in parentheses, raised to the fourth power. So we see that we have a number 4 here and we have a number 4 there. It's even. So that means this equals to the absolute value of f to the third power. The absolute value of f to the third power. Absolute value is just a measure of distance. I'm not going to go into absolute value here, but it's just a measure of distance, and we can't really have negative distance. It doesn't really make that much sense. Anyways, so because this is equal to that, right? So that's how I got that one. This times this is 12, right? Absolute value of f to the third. So now that you have your absolute value of f to the third, is just going to equal f to the third power. So now we go ahead and multiply f to the third power by 3. So our answer is going to be 3 times f to the third power. 3 times f to the third power. 3 because the fourth root of 81 is 3, and you saw how we did this one. That's going to be the answer for number 1. Let's go ahead and do number 2. I have the cubed root of 27 a to the third power times k to the fourth power. Again, we can separate these values the way we did here. So we have the third root. I can rewrite this as a third root of 27 multiplied by the third root, the cubed root of a to the third power multiplied by the cube root of k to the fourth power. That's a 4, by the way, to the fourth power. So what number times itself 3 times is going to give us 27? That is going to be equal to 3, right? Because 3 times 3 times 3 is 27. All right, and now we have this one. This is odd, so that means this is going to equal to the value inside of the cube root. So that is going to be a. Let's just put it here, a. And now this one, we can rewrite this one as the cube root of k to the fourth power is equal to the cube root of k to the third power times the cube root of k. All right, so we have that, the cube root of k to the third times the cube root of k. there's going to be not really there's just going to be a number 1 here, a number 1 exponent. You don't have to put it there, but I'm just going to put it. So what this means is that when we multiply these radicals, we have to add their exponents. So k to the third times k to the first power is going to be equal to k to the fourth. So this equals that. And then we see here that this is odd, so this is going to equal the value inside of the cube root, and it's going to be k. And this one we can't really simplify it any further, so it's just going to be the cube root of k. All right, so we have k times the cube root of k. And now we can pretty much put all of these together, the 3, the a, and this. So we have 3 times a times k times the cube root of k. So we have 3 times a times k times the cube root of k as the answer. Make sure you didn't do any mistakes. It looks good so far. So that's going to be the answer to number 2. Let's go ahead and do number 3. We have, sorry about that. We have the cube root of n to the 4th power times b times the cube root of 27 n squared times b. We can rewrite it individually, or we can multiply it all together and then rewrite it individually, but I'm going to choose to multiply it all together and rewrite it individually, because that makes more sense to me. So let's go ahead and do that right now. We can rewrite this as the cube root of 27 times, we have n squared times n to the 4th. What is that going to equal? That is going to equal n to the 6th power, because we add the exponents when we multiply. N to the 6th power. And then what else? We have b. There's b here and b there. B times b is b squared. B squared. So now we can break this up and pretty much solve. So now we have the cube root of 27 times the cube root of n to the 6th power times the cube root of b squared. All right, so what number times itself 3 times is going to equal to 27? Again, it's going to be 3, because 3 times 3 times 3 is 27. And now we have this one. Let's go ahead and rewrite this one. So the cube root of n to the 6th power is going to be equal to the cube root of n to the 2nd power times parentheses 3rd power. So this n to the 2nd power raised to the 3rd power. And when we multiply this kind of exponents, an exponent pretty much in parentheses raised to another exponent, you multiply these two. 3 times 2 is 6, right? It's like that. You multiply this equals that, right? So we have n squared. So this is odd, a 3 here and a 3 there. That means it's going to be equal to the value inside the cube root, which is going to be n squared. So n squared. All right. So now we have pretty much n squared for this one. N squared. So on this one, there's really no way to simplify it even further right now. So we're just going to leave it as is. So it's going to be the cube root of b squared. So your answer here is going to be, you multiply all of these together to get 3n squared times the cube root of b squared. Make sure everything makes sense. Everything is, no mistakes have been done. 3n squared times the cube root of b to the second power. That is how you do number 3, but I have 2 more examples to show you right here. Let's just flip this over. Just put this here. All right, number 4, we have the square root of 27 plus the square root of 12. The way we can do this is by pretty much using a factor tree for 27, so we can simplify this one, and we're also going to simplify the 12. A factor tree for 27, that is going to equal to 3 times 9, because these two values are going to give us 27. And what two values will give us 9? That's going to be 3 times 3. So since this is a square root, we need to look for the perfect square of, we need to look for the perfect square of two twins, let's say, that will go in the group. We have 1 3 here, and we have another 3 there. 3 and 3 are the same number, so they are, in this case, I'm just going to call them twins. They're twins, so they belong in a group. This 3, since we're only looking for groups of 2, this 3 is an outcast. It's not going to go in the group. So this translates to 3, let me write it here, 3 times the square root of the lone number 3. So the square root of 27 literally equals to 3 times the square root of 3. Let's go on to this one, the square root of 12. We have 12. What two values multiplied will give us 12? We have 2, and then we have a 6. But we can continue simplifying the number 6. 2 times 3. So what we have here is, we have basically what two numbers make the perfect square. We're looking for groups of 2 of equal numbers. We have 2, and they're the same. They belong in the group. This one does not belong in the group. It's not the same number, and it doesn't have a pair. So this equals to 2 times the square root of the lone number 3. So now we can add. We have 3 times the square root of 3 plus 2 times the square root of 3. This is going to equal to 5, because 3 plus 2 is 5, times the square root of 3. My pen is running out. 5 times the square root of 3. So now, let us move on to the last one, number 5. The square root of 16w to the 5th power plus the square root of w. So, again, basically, what number by itself, what number multiplied by itself is going to give us 16? That is going to equal to a 4. Well, a 4, right? We have a 4, and we also have the square root of w5. Since this is a perfect square, we can take it out of the square root. So now we have a 4 times the square root of w5. Obviously, we have the w here. Let us rewrite the w5. So this square root of w5 is equal to, remember, when you multiply exponents, you add them. So the square root of w2 times the square root of w2 times the square root of w. All right? So because this is equal to this times this times this, let's put a 1 right here. This 2 times, when you multiply exponents, 2 times 2, that's 4, and 2 times 2. 2 plus 2, that's 4, plus 1, that's 5. This equals to that. So that is how we rewrite this one. That's how we rewrite this one. And basically we take the square root. This is obviously going to equal to w. Square root of that is going to equal to w times the square root of w, because we can't really take the square root of w. It's not a perfect square. These are, but this is not. So w times w is going to equal to w squared times square root of w. So now we have 4 times w squared times the square root of w plus the square root of w. We can go ahead and simplify this even further by factoring. We see that both of these terms, this one and this one, have a square root of w in common. So we're going to take the square root of w and multiply it by 4w to the second power plus 1. 4w to the second power plus 1. Why? Because if you do the distributive property, the square root of w times 4w to the second power, we get 4w to the second power times the square root of w, because you multiply this, plus the plus sign, you multiply the square root of w plus 1, you get the square root of w, which basically equals this. So this will be our answer. All right, and that's it.